So I apologize you all have to listen to me twice today, but it just happened they ended up on the same day, even though they're different tracks. So this is a topic of my postdoctoral fellowship, which is funded through the National Space Biomedical Research Institute, through NASA, or the National Aeronautics and Space Administration. And NASA is particularly interested in kidney stones because astronauts are thought to be at an increased risk because of changes in bone metabolism, dehydration, and stasis that all occur in space. And so, thank you for the introduction. You saw part of this slide before, but kidney stones affect 1 in 11 Americans, with the global prevalence increasing worldwide. The current gold standard for detection of kidney stones is computed tomography, and in fact it's used heavily in the US, though I've heard other countries rely more on other techniques. But the problem is it exposes patients to ionizing radiation. So if you have a patient that comes in with stones and is a repeat stone former, and you're monitoring the growth of the stone to plan out therapies, et cetera, you're exposing the patients to significant amount of ionizing radiation. Beam-mold ultrasound has been used in other countries, but there's a variable range of reported sensitivities, from some as low as 30% all the way up to it performs as well as CT. And on your right are just a few pictures of some kidney stones. So this color-Doppler ultrasound twinkling artifact has the potential to improve kidney stone detection, but it doesn't appear consistently when it's been tried to be used in the clinic. So it was first discovered in 1990 by a team led by Dr. Amuni, and they found this rapid color change that showed up on kidney stones. Since then, there's been a lot of research into the mechanism of the color-Doppler ultrasound twinkling artifact, with some thinking it has to do with the ultrasound processing, a phase jitter in the ultrasound signal, and others thinking it has to do simply with the interaction with the stone. We're going from soft tissue to a very dense object. There's potentially some ringing. And so just to orient you, if you're not familiar, you can see the outline of the kidney in the grayscale. The collecting system is the dark area in the middle, and then the kidney stone is that twinkling area below. You can see some interference as the video repeats. Our team at the University of Washington recently came up with this crevice bubble hypothesis to describe twinkling, namely that there are stable crevice bubbles or gas pockets between the kidney stone surface and the air. And one way to test this is if you increase the ambient pressure. Because it's a stabilized crevice bubble, instead of dissolving into the liquid, it actually causes an inflection of the surface, and so that you get a smaller crevice bubble, but that the crevice bubble is still present, so that when you release the pressure, you still have a gas pocket present. And here's just a scanning electron microscopy image of the kidney stone surface, where you can see that at least for this calcium oxalate type of kidney stone, there are a lot of potential areas where crevices could form. So, as I kind of alluded to, we tested that in an overpressure chamber. So we used a Verisonics ultrasound system, which is a programmable ultrasound system that allows you to completely get back your radio frequency signal in raw form. You can do the beamforming and reconstruct the image so that we can ensure that nothing in the black box of ultrasound from the past is what causes this artifact. And you use a commercial imaging probe. And then we also combine that with the hydraulic pressure chamber. Now this is an aluminum-walled chamber. The transducer is lensed in through an acrylic lens, and then the stone is just sitting on an acoustic absorber to prevent reflections within the chamber. And then using a hydraulic hand pump, we can then increase the pressure in the chamber, or then release the pressure. What we found supported the crevice bubble hypothesis. So this is a plot of twinkling power amplitude, which we can get from the raw radio frequency data, and then just basically take the amplitude of the Doppler signal versus time when we change pressure. So at 1 atmosphere absolute, or standard pressure, we get a pretty strong twinkling artifact. When we increase the pressure up to 4 atmospheres, we get a sharp decrease, and so the twinkling disappears. And upon return to the 1 atmosphere of pressure, we find that twinkling also returns, albeit at a slightly lower amplitude. And this is for an 8 millimeter ex vivo comstone, which is calcium oxalate monohydrate. However, there's some difficulties in this because if we repeat the experiment within the same stone, this example happens to be with a different imaging transducer, but we've repeated with the same, we find that the threshold to change twinkling isn't always consistent. So in this case, we have a similar amplitude initial twinkling. Twinkling goes away not until 6 atmospheres instead of 4 atmospheres absolute. And so part of this was determining why this occurs, what's the difference between individual stones, is it simply the architecture? And so that led me to a different sort of technique of, well, let's try to grow our own stones then. Basically, I wanted to create an artificial kidney in the lab to create kidney stones, with the goal of, can we get twinkling to be extremely consistent for our etiology studies so we can determine, which will aid towards understanding what causes stone formation, but also aid in determining what causes twinkling and how we can use twinkling, or enhanced twinkling, for stone detection. And so I used a stone farm that's been developed actually here in the UK by Dr. John Kavanagh, where you put seed crystals in seed stones in an artificial chamber, feed it with an artificial urine solution supersaturated with a calcium oxalate so that crystals form on the stone. And up in the right corner here, you can see we do get crystal growth. It does take quite a long time. But upon micro-CT imaging, we find that the grown crystal differs significantly from the seed stone. Now, this is actually quite interesting because it suggests that not only are supersaturation conditions necessary for stone formation, but also something else. Whatever that something else may be, we're still investigating. But it's just a side topic I'm working on at the moment. So hyperbaric pressure decreases twinkling. What if we go the other way? In theory, it should expand the bubbles, enhance twinkling. And what we found is that is the case. You take twinkling at a low amplitude, you reduce the pressure, so now we're at like 0.2 atmospheres absolute. You see that twinkling increases. There's some variation as we slowly decrease the pressure, but basically twinkling returns to its approximate initial levels. These studies are actually being leveraged for a current human hyperbaric study that we're currently recruiting for. This is in collaboration with a Virginia Mason hospital because they have a multi-person hyperbaric chamber. And we're trying to recruit 8 subjects to expose them to 4 atmospheres absolute pressure, which takes about an hour, and we're going to do continuously monitor of twinkling. And so this is a really exciting study. The question has always been, are the bubbles then present in situ in the human body, or are we introducing the bubbles when we remove the kidney stones? And so this would be one of the first instances that I know of where stable bubbles could be present in the human body. So the question always comes, if you think it's bubbles, why can't you see them? And so I set up this high magnification, high-speed photography experiment where I tried to look for bubbles on the stone surface. So I'm using our Photron high-speed camera using a high magnification lens so that I can get resolution on the order of several hundred, or less than several hundred, a few micrometers. And despite several hours, I found one evidence of a bubble growing when the stone was exposed to color-Doppler ultrasound. And you can see it. See it right here? It grows very slowly over a 40 millisecond period. But right now it's in its collapse stage. If we wait a moment, you can see, if you watch carefully, it's slowly growing. It reaches its maximum size approximately, and then begins to collapse. However, despite repeated experimentation, I was only able to find one bubble. So that's not super conclusive, but it led to some other results. One of the things I found actually during this study was that bacteria were on our kidney stones. Granted, this is a common yeast that we likely introduced sometime during the removal or later, but it came to the idea is maybe bacteria form these bubbles on the stone. So we've done some preliminary studies where we've gotten really fresh stones from our urologists and sent them off for bacterial analysis after determining whether they twinkle or not, or show the twinkling artifact. And we found that there actually could be a relationship. In the stones that did not twinkle, the only types of bacteria we found were nosocomial, or types of bacteria that are found in hospitals and aren't likely to actually be in the human body. And so there could be this relationship. The problem was only two of our 6 stones didn't show the twinkling artifact. So it's still a low number, but we're currently following up on that. One other way to image bubbles is using shock waves. So I set up this really complicated experiment basically to determine, so we know that shock waves can be used to introduce bubbles to the stone. Can we create just a few bubbles, and can we then see twinkling as verified with high-speed photography? So on the left side of the image there, you can see that's part of a Dornier HM3 shockwave source that we have the head put into this water chamber so that we can precisely control everything. We have lighting from above and the high-speed camera, and then we also have the ultrasound machine there. And if you look at from the end of the tank, you can then see the lithotripter head and the imager transducer coming up from, or looking down from above, and then the front of the high-speed photography. We placed the stone in such a place that it was prefocal and off-axis, such that we got a long negative tail without the without the large shock. And so the shock amplitude is less than 1.5 megapascals, but our negative pressure that should expand the bubbles is almost 3 megapascals. And here's a quick image of what we found. With this calcium oxalate stone that did twinkle, we found that when the shock arrived, granted you get some reflections, so some twinkling off the stone, but we were able to make the twinkling very strong. And we were also able to find some bubbles on the stone that weren't present. And then, of course, after the shock decays, twinkling's back to normal. More interestingly, on this artificial stone that did not twinkle initially, we could actually introduce bubbles and cause twinkling to appear on these stones. And this is actually, we're investigating how we can get this negative offset to be able to actually create bubbles on stones. And if we could do that in a safe manner, we could use this to enhance twinkling for all stone types. One final study has to do with the effect of increased carbon dioxide. So we know that carbon dioxide dissolves preferentially in liquid, about 20 times more soluble than oxygen or nitrogen. On the International Space Station, carbon dioxide levels are at 10 to 20 times what we find on Earth, so they're breathing significantly more carbon dioxide than we are. If twinkling is due to bubbles, it's reasonable to assume that more carbon dioxide in the urine would potentially influence those bubbles. And so what we did, we implanted swine with stones that twinkle. We had them breathe carbon dioxide for about 2 hours or until their oxygen saturations reached dangerously low levels. We'd switch them back to oxygen, see if twinkling returned, and then repeat that change of carbon dioxide, then oxygen. And while we did this, we would monitor changes in the twinkling artifact, but also changes in the blood and urine chemistry to see if there was a change. And this was just a recent study. We've done two pigs so far, but basically what we found, twinkling was strong when they breathed pure oxygen. About 15 to 20 minutes on carbon dioxide, twinkling was decreased and went away after 60 minutes. But upon return to pure oxygen, twinkling would return again after 15 minutes and was even restored to its initial levels after about 30 minutes. Interestingly, we found very little changes in the chemistry of the urine, but there was, of course, large changes in the blood oxygen saturation levels and also the carbon dioxide levels in the blood. And so this also supports the twinkling artifact being from bubbles and further suggests that in space, the twinkling artifact might not be a successful way to detect kidney stones, or potentially we need to lower the carbon dioxide levels on space travel vehicles. So as I've been saying, this all supports the bubble hypothesis to describe twinkling because overpressure decreases twinkling, under pressure or hypobaric conditions increases twinkling. While the bubbles are not visible by techniques we have available, we can use shock waves to enlarge existing bubbles, and in fact, upon repeated exposure, we find the bubbles expand from the same location with each pulse, which further supports that they're present on the stone. And finally, inhalation of carbon dioxide actually suppresses twinkling. And so the end goal of this project is to use bubbles to enhance twinkling. So now that we understand the mechanism, we're working on developing techniques that utilize this bubble hypothesis to enhance twinkling so it can be in all stone types and be a robust diagnostic tool. So I'd like to thank you for your attention and would take questions. So there is one model in pigs that grows stones, but it takes months of feeding them a special diet. So we use human ex vivo stones to implant for our studies. We use swine because their kidneys are the most similar in anatomy to humans. And so unfortunately we don't have a model that actually grows stones. I amend that. Cats and dogs are known to get stones, cats in particular. Our university won't let us do research on cats and dogs. So our second best model then is swine. Go ahead.
The twinkling is due to the air pressing up against the solid stone. Is that correct?
The scattering of the ultrasound signal from that air to, interface.
Have you given any thought to using that mechanism as a contrast agent similar to microbubbles where you can actually compress that within a fluid?
That's a great question. So we have looked at actually using targeted microbubbles to enhance twinkling. We run into issues then of, particularly for space travel, of stabilizing those bubbles, etc. As far as bubbles in other contexts, we are actually interested in looking at decompression sickness, so bubbles that arise in joints. And we have looked at some of the microbubbles that are, I believe they are approved in the European Union for use, and those do twinkle. We don't know exactly the level, so we're kind of fiddling with parameters to see what level or concentration of microbubbles is necessary to cause the twinkling to actually be evident. So I hope that answers your question. Well, thank you.